So in the last video we started to develop our theory of waves, and here we're going to see what happens if two waves interfere. Now it turns out that mechanical waves obey superposition. Which means that we can treat one wave as if it were the only wave in the universe and solve for it. And then we can solve for the other wave as if it were the only wave in the universe. And then to get what the net thing that's going on is, we can just add the two together. So let's take a look at a pulse two pulses going down strings going into head-on collision. Now, at first, they will just get closer, but now what happens when they start to overlap? So let's get to the point of overlap. Well, the first wave would want to do this, and the second wave would want to do the same. So that would have the effect of just doubling it over like that. But then as you go on, it looks like the waves just passed right through each other. So now they're heading out the other way. Oops. Like so. So at every point in space, just add up the contributions of the two waves, and you will get the final result. So the two big cases of interference I want to take a look at are constructive interference. So here I want to look at the history graphs for two waves. Let's say you have two speakers and you are sitting at the sweet spot between the two speakers. What that will mean if you're in the sweet spot is that whenever you're hearing a crest come from the one speaker at your location, you will have a matching crest coming from the other speaker at that same location. And ditto with the troughs. If you have a trough coming from the one speaker, you have a trough coming from the other speaker. So that's what happens when you set the sweet spot of a speaker, of a stereo. So the net result that you hear is just the sum of the two waves like that. What about destructive interference? This turns out to be the basis of noise-canceling headphones. Sorry about that. So here, again, if I plot a history graph at your location, or if you've ever thought you were sitting at the sweet spot, but the sound of your stereo sounded really muddy, probably what happened is you wired one of your speakers backwards. And so as a result, coming from the one speaker, it looked like the history graph looked like this, but from the other speaker, because you wired it backwards, it looked like that. So now what you do is at every location, you add them together. So here, crest plus trough is going to give me nothing. Trough plus crest will give me nothing. Nothing plus nothing gives me nothing. Halfway up, halfway down. It always adds up to nothing. So sometimes that's a feature. So for instance, with noise-canceling headphones, one popular design for noise-canceling headphones is to put a microphone on the outside of the headphone enclosure. It listens to the ambient noise. It then electronically adds the negative of the ambient noise to the sound you're listening to, the sound wave you're listening to, and times it such that when the ambient noise actually makes it to the speaker, that's when the modified waveform that has the negative of the ambient noise is being produced. Add the two together and you cancel out the noise and leave yourself with just the sound that you wanted to hear. Now, another example of this would be beats. If you've ever heard someone tune a guitar, for instance, or a piano, you'll usually see them take out a tuning fork, strike the tuning fork, which will make a very, very well-known frequency. And then what they'll do is they'll start playing the corresponding string in the case of a guitar, or key in the case of the piano. And they're not per se listening to the difference in the sound. I mean, they are, because they need to know if it's higher or lower than the tuning fork. But to tell how close they're getting, they're listening for the beats. This is, when you hear that, you'll hear sort of like a wah, 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 wah kind of a thing happening if you have two closely spaced frequencies. That's the beat. So I'm going to try to draw this, and it's probably not going to go very well. So there's one sound wave, and then let's see, I'm going to need this one to do something like that. There we go. So we've got sound waves of differing frequencies here. And here the difference is actually quite large, but it's because I'm a poor artist. But the point is that some spots, the two waves are doing the same thing at the same time, and so they will constructively interfere. But like, say, right here, they're doing opposite things at the same time, and so they'll destructively interfere. So the net result is a wave whose frequency is intermediate between the two. Yeah, right. This may take a few tries. Well, I tried. It's a wave whose frequency is intermediate between the two, but the loudness of which I'm just indicating by drawing an envelope here that the wave could fit in, oscillates at some frequency of its own. If you're really, really good with your trig identities for adding or subtracting angles inside trig functions, you can work out that the frequency of oscillation that you're hearing turns out to be the average of the two source frequencies, say the tuning fork and the guitar string. And the beat frequency turns out to be the absolute value of the difference of the two frequencies. So the closer the two get together in frequency, the less frequent that wah, wah, wah kind of sound is. So just to do a quick example of that, let's say you're trying to tune a piano that's fairly out of tune. Concert A is generally accepted to be 440 hertz, except when a conductor feels like it isn't. But let's say it's 440 hertz. And then let's say that our out of tune piano really out of tune piano is at 446 hertz. Okay, so the frequency, if you were to strike a tuning fork and then hit A on the piano, the frequency you would hear would be 1/2 of the frequency of the tuning fork plus the frequency of our out of tune piano. So the frequency you'd hear would be 443 hertz. But that warbling frequency, the wah, 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 That would be the absolute value of 440 hertz minus 446 hertz to give you 6 hertz. So you would hear 6 warbles a second, and a piano tuner would be going, man, what happened? Did you have one of those conductors who really didn't like 440, really didn't like the internationally agreed upon standard of 440, or have you just not hired me in a very long time? Alrighty, so we will pick up more on waves the next time as we start to look at how they interface with human hearing. Catch you on the flip side.